Hello, welcome to 2 a.m. Philosopher. This is the very first video, and for the very first video, we have a special guest, Mo from Zoomer Action.
Hello, everyone. I'm real happy to be here.
Today, we are going to talk about three topics: LoRA, function decorators in Python, and RFID. So let me kick us off with LoRA. It's a machine learning NLP. Well, not necessarily NLP, but I'm working on an NLP task that requires fine tuning. And for that, I read this paper, Low Rank Adaptation of Large Language Models. And so I'm very quickly gonna explain. And Mo, please ask me any questions as we go through this. So let's first read the abstract. So an important paradigm of natural language processing consists of large-scale pre-training and general domain data and adaptation to particular tasks or domains. As we pre-train larger models, full fine-tuning, which retrains all model parameters, become less feasible. Using GPT-3, 175 billion as an example, deploying independent instances of fine-tuned models, each with 175 parameters, is prohibitively expensive. So yeah, like I ran through this problem as well. For the model that I wanted to fine tune, which was Llama 2 7 billion, it requires so much resources and GPUs to fine tune and the entire model and change all the parameters. So what they did, they proposed a low rank adaptation, or in short LoRA, and they freeze the pre-trained model weights and then inject trainable rank to each, and only for the transformer. Like in this paper, they went over the transformer architecture, and they are arguing that greatly reduces the number of trainable parameters. And they cut down the GPU memory requirement by 3 times, which is crazy. And they showed that there is no additional inference latency. Okay, so how this works? I think this picture is pretty amazing. They have the pre-trained weights W, and it's a D by D matrix. And so on the new task that we are fine tuning, we want to change these weights, and their intuition was that the delta W is low rank. So they thought, okay, if it's low rank, that means we can decompose it into two matrix. So delta W equals AB, and that's what is shown here. So we have the A matrix that is of rank R, and a B matrix. And here you see that they initialize it to be from normal distribution, and B is initialized to be 0, and then you change the parameters and backprop while this W is completely freezed. And so let's quickly. So yeah, their hypothesis is that the change in weights during model adaptation also has a low intrinsic rank, and so the key advantages is that they do not need to calculate the gradient to or maintain the optimizer state for most parameters, and that's why it requires so much less memory, GPU memory, which is pretty expensive.
Excuse me, can you please, for the audience, repeat why we need less memory?
Yeah, so when we have 175 billion parameters, let's say in the case of GPT-3, we want to deploy that let's say 800 GPU, which is the top, the best GPU out there, can hold anything between 40 gig of or 8 to up to, let's say, 80 gig of VRAM. That's not enough to keep track of both the parameters and the state of the optimizer. Adam that everyone uses, this does require so much keeping track of so much things in the state, and that requires VRAM, and that's expensive. And so if we it saves us a lot of money if we can do the fine tuning on less resources. And what is amazing about this paper is that it shows that fine tuning with LoRa actually converges with full fine tuning. That's something we're gonna get to shortly. Thanks for the question, though. So first, they talk about why aren't existing solutions good, and the first one is we previously had adapter layer solution and optimizing the prompt, and they show that the adapter layer, which means like adding more layers, reduces the inference speed or adds inference latency, which makes sense because now it has to go through more layers. And the second one, optimizing the prompt for your specific thing is they argue is pretty hard.
What does optimizing your prompt entail?
So basically, it's a technique that these guys, I think, introduced. That it has prefix tuning, so they add layers at the beginning, and based on the task, it helps with but basically changing the prompt through those added layers in the beginning, and fine tuning for that task. But they argue it's hard and it's difficult to optimize, and the performance changes non-monotonically in the trainable parameters. But yeah, I don't know enough about a prefix tuning or optimizing prompt, so whatever I said, take with a grain of salt. But good question. Yeah, so here they argue that LoRa roughly converges to training the original model, which is pretty interesting. And they show a bunch of results that I'm gonna skip over, but one thing that was pretty interesting, it was here. So they tested in changing different weights, and then in transformer architecture we have query key and value matrices, and they showed that if we only change the query and value, we can almost get the same same loss as if we were to fine tune on all these matrices. So Q stands for query, K is key, V is value, and O is output. And another interesting thing was the rank of the matrix. 8 is performing even better than 64, which suggests that probably delta W has a very small intrinsic rank, and then they calculate some similarity stuff, and they find out that the first component of 8 and 64 are very similar, which suggests that the first direction when they do the SVG is very similar, and they say that also that shows that the adaptation matrix is very low rank, and then they also argue that probably W is probably low rank as well. And then I maybe quickly go over the conclusion as well, which basically says that if we were to do this, have these delta W's for different tasks, we can deploy things more easily. Why? Because we froze the W matrix, so we can just have a bunch of delta W's for different tasks, and then switch to the one delta W depending on the task, and use sort of the same W, which helps with deploying. And for future works, they said that W could be rank deficient as well, but it has to be, you know, we have to work on it more and figure out if it actually is. But they are pretty interesting paper, and I saw so many people start using LoRa. So if you don't have that many resources and you want to fine tune something, I highly suggest that you read this paper. There's another paper called QLoRa that maybe I go over it next in the next video, but they also add quantization on top of LoRa, and they show that you can use that if you like have very limited resources for fine tuning. But yeah, so let's switch to the next topic if you don't have any questions for now.
No questions for now.
Perfect.
But absolutely look forward to seeing the next video about QLoRa. As Q stands for quantize, I believe that makes the fine tuning way by LoRa more interesting, since we have smaller parameters and probably we will have more interesting outputs if we fine tune with less amount of effort.
Yeah, definitely. It's I know that if you know just wanna don't have only have a GPU and want to mess around with these big language models, definitely QLoRa it's what you need, and we hopefully go over that soon. All right, so next we have the decorator. So recently we both saw this in an interview that they talked about this, and I didn't know, so I decided to take a look at the function decorators. And so imagine that in the case that they suggested, imagine if you have like a lot of function that you want to calculate the time for, then what you do, you add this decorator, I call the timekeeper, and then you have a wrapper, and you return that wrapper, and the function, the timekeeper is taking another function, and you print the date, and you call that function that is passed, and you print the date after again. Let's say like you wanted to print the date before and after every function that is called in a program. And then you can add this timekeeper on top of all the programs, and when they're called, the time is printed for them, instead of, you know, just keep adding these two lines in every single function. You can just add the add timekeeper. So let's do something. We can say def question printer decorator, maybe that takes a font.
I suggest for our viewers, can we make the font a little bit bigger?
Yeah, absolutely. So let me, okay, hopefully now it helps. Thanks for the suggestion. He's been doing this for a long time now, so he knows better about the producing the videos. Okay, so let's actually call this fun, because this video hopefully is fun. And so this function is prints A and B, and so we have to return the wrapper, and so question printer. So yeah, actually, so rename it to last decorator, and then here have the question printer. And so what this function does, it just prints question mark. And now if I have this last decorator and I call this question printer, you see that A and B is printed. So let's actually, for the say awesome, also have this last decorator, just to show that all of them will have this A and B. So you see, like, A, 2 a.m. philosophy. Oh, I forgot to. Sorry, I forgot to add the parentheses. Yeah. You see, like for all of them, we have A and B after and before and after each of these print statements. So pretty cool. And do you have any questions?
No, but I just wanted to go over this again. The decorator architecture, as you can see, obviously this is Python, so this is a feature of Python. And what else can we say about this? So, where would you use this?
Honestly, like if you have a lot of functions and you want to do something very generic, I think this is the best example. Let's say like want to keep track of time and or see like how long your function took. You could, take this time, minus it, print it, and it can be it can be printed for every single function, and then you don't need to add like print statement all over or make, let's say like you want to change the logic, then you have to go to like 20 different places and change these two lines. Because if you have one function that does it for you, it makes the code much more cleaner, and so it saves you a lot of time. So it's definitely something good to know. It is asked in interviews as well. So
I have one more question. Can we have multiple decorators for, like, for example, the function, say, channel name?
great question. I don't think so, but let's give it a try. So let's see if we can have the timekeeper and the last decorator. And actually we can. I think we tested this before. And
Yes. So yeah, if you can look at this, it kind of gives you this nested way of your functions. As you can see, you
so
have
we have
A
A.
and B wrapping over the time.
Yeah.
And
Okay.
then
Cool. So yeah. So it's first last decorator. So it's first A, and then the timekeeper. So which prints the time, and then the function is called once, only once, and then we have the second time from the timekeeper, and we have then the closing from the last decorator. Yeah, it's pretty interesting. I didn't know that.
I have one more question.
Yeah.
We have seen this keyboard of @ being. Have you seen this keyboard of @ being used other places? I have seen it being used for like static functions.
Yeah, it is used. I think it's
Can we
like
check that?
annotation. It is used for sentence,
Advanced.
but it's like
So,
any time you want to use annotation, you use that.
so is that like a general thing in Python?
I think so. Yeah. You can
So if you
configure
call it a static, it probably just wraps it in somewhere else in the Python library, maybe.
Yeah,
And
it's
then
a good topic for maybe a future video how this add sign works and how Python handles that.
fair enough, fair enough.
So for that, even either check this channel soon, or it would be in Zoomer Action. One of us will
We'll
take a look
cover
at this.
this for you.
All right,
Alrighty.
perfect. Check this website for more details. I took some of these examples from there, and I will link it in the description as well. Okay, so last topic is, if I find it, is RFID. This is something I was watching the
Oh, my bad.
I was watching the Neuralink video, and
Can you explain for our viewers what was in the
oh yeah,
video?
of course, it's pretty interesting as well. So the Lex Fridman, definitely check this guy. He has amazing podcast. Maybe you already know him.
Who did he interview?
So he interviewed a bunch of people from Neuralink, including Elon Musk and the other co-founder. And so the co-founder, who is very an expert in all the technical details, was talking about RFID at some point in the interview. It's an 8 hours interview. I highly suggest you watch at least part of it.
Did you watch it for yourself?
I was around maybe 4 or 5 hours of it.
I see.
I'm planning to watch more, but yeah. And I was fascinated with this, so I took a quick look, and so basically RFID. All of us have, or hopefully most of us have seen cards that can be tapped. Let's say like when you're buying something, or when you're entering a house, or dorms, hotels, and whatnot. So these card readers, there's a reader, and there's a RFID reader, and there's a card itself. They call it RFID tag, um, and what it has, it has an antenna, and it has basically a small coil. And what happens is that the RFID reader,
Sorry, what is the coil?
so it's like it's used when to charge. So let's see.
Is the coil on the card or is it on the device that it scans?
Let's see. No, I think it's on the tag, RFID tag.
Oh,
I cannot find a good. Yeah, I cannot find a good picture, but basically it doesn't have a battery.
Mm-hmm.
So how it sends stuff through antenna is that it gets charged from the RFID reader, and we quickly read through the Wikipedia introduction. We'll see there as well. But it has a very small memory. In one of the YouTube videos I saw, I maybe find it on the link in the description. Let's say it's 64 kilobyte of memory, and this is usually a pointer to somewhere else. So that information is communicated through antenna. The RFID reader gets that information, and it's usually connected to the internet, so it can use that information, and it's a pointer, so it looks it up. In this case, in this example that we see on the right, maybe it's a database entry or key, and it looks up the database. And But yeah, it's pretty interesting. So let me quickly also read through this section. So it stands for radio frequency identification. It uses electromagnetic fields.
Mm-hmm.
It identify and track tags attached to objects, and it has a tiny radio transponder,
Yes.
and a radio receiver and a transmitter. And when triggered by electromagnetic a pulse from nearby RFID reader, the tag transmits digital data, usually an identifying inventor number. So like that's the basically that is what is stored in that 64 kilobyte, because that's not enough memory to store anything, too much information. So you just store the pointer, the reader keeps takes care of the rest. And here it talks about a bunch of things, that it is used in many it has many use cases, and it was an $8 billion, roughly $9 billion in 2014, which is
Right, and
which is
$9
crazy.
billion market for the tax.
For the
whole system.
whole RFID market. I don't know how they define it, but yeah.
Does that include like also the chips inside your phone when you pay? Is that an RFID system? I believe so, because that's how the system looks like.
Maybe. I don't know. It could be.
Okay.
I don't see yeah.
But like we obviously have seen these tags in like library books, clothes that you buy.
Yeah, for me the main use case was my dorm. I open it.
Right.
Yeah, I was always wondering how they figure it out, because like the first day they quickly.
Right.
Yeah, I think they add the pointer probably to your card, and that's how it's authenticated. The
Right.
reader is connected to the internet, quickly checks, you know, through that pointer whether you have the authentication or not to use to enter the building. But yeah, pretty cool stuff. Any final words?
Um,
Maybe you can promote your channel.
I'm good, thank you.
All
We're
right.
doing pretty well there.
All right, awesome. Check out Zoomer Action, and I think that's it. That's the
That's it for this video.
first video of 2 a.m. philosophers, and we covered LoRa, decorator, RFID, and yeah, again, take everything with a grain of salt, but pretty cool stuff, and hopefully we will be back soon.
Thank you for watching this. See you next time.
See you next time.